Hello, today we're going to introduce a new unit, that kinetics, so the rate of reactions. So what is kinetics of reaction about? We are trying to answer some question. Why are certain reactions much slower than other reactions? So for example, you know that you're familiar with the fact that there are different kind of glues and the time that it takes for the glue to cure is quite different. There are some glue that are almost instantaneously bonding, while others would take maybe several hours. Why putting food in the fridge makes the storage longer, make the food last longer? Or why does, for example, seafood deteriorate much faster than meat? If burning wood is an exothermic reaction that gives off heat, how come to start we need to actually go there with some fire? And sometimes when you are in, camping, you know that to start a fire may be quite a hard job. So you might remember that I brought to class potassium, metallic potassium, and we observed the very intense and quick reaction of potassium with water. It was basically an oxidation where potassium was giving off one electron and it was producing hydrogen. The solution was turning pink because we were making potassium hydroxide as a product of the reaction, and I added phenolphthalein, so the solution was turning pink. And it was also giving off hydrogen, so you could see the little piece of potassium kind of running around like a little rocket in the solution, and it was an exothermic reaction. The heat was actually enough to ignite the hydrogen, so we could observe a flame on top of the little piece of potassium as it was reacting, and the flame was colored in purple because that's the color of the potassium flame. So we saw that reaction was quite fast, but iron oxidizing and forming rust is kind of the same reaction, is an oxidation, loss of electrons, but that takes hours or sometimes days. So how come the reaction have such a different rate? So first of all, we want to define what is reaction rate, right? So you're familiar with the rate of an object, like the rate of a car. So that would be how many miles or kilometers you are covering in a certain amount of time. So it's the ratio between the distance covered and the time interval. So I'm sorry, we can represent the distance covered as a delta D. So that would be the difference between the final position minus the initial position of the car. So if you're going to driving to Madison, and by the time you're in Madison, the miles that are on the highway sign says, let's say 75, and you're starting from Platteville where the mile number is 20, you know that you have travel along 75 minus 20, 55 miles. That's actually going to Madison is longer, but I'm just making up numbers here. So it's always finals minus initial. Similarly, for the time, right, you look at the clock when you leave, you look at the clock when you arrive, and you go finals minus initial. That takes you the amount of time that it took to travel. So it's always finals minus initial. For reaction rates, it's very similar. We just measure different things. We don't measure the distance traveled, we measure the amount of product that we have made. So the change in the concentration of the product. Or we can measure the amount of reactant that has disappeared. And that would be the change in the concentration of the reactant. But it's always measured as finals minus initial. So the actual variable that we are measuring is molarity, so moles over liter. So we're going to write it like that, right? With delta A in square brackets at the top. That means change in the molar concentration. So from this moment on, we are going to use this symbol, formula of a compound in between square brackets to indicate the molarity of that compound. So moles over liters of solution. And the change is going to be the final minus the initial. Okay, so now I would like you to stop the movie and the video and just follow the link and go watch a movie, and then you can come back for the rest of the PowerPoint presentation. So to explain rate reaction, we want to have a model, something that allows us to have sort of a picture in our brain and better understand what's going on. This model is called the collision theory model, and it could be summarized in a sort of a motto that is, you can't react if you can't collide. So the reaction is the result of a collision between two molecules. So we can kind of make a comparison, that's where the picture is coming from, with a billiard ball, and the balls that we have are defective, so they have little cracks. So what happens is that sometimes when they collide into each other, they're going to break. But not all the time, just every now and then. So what would make this breakage more likely to happen? Well, if you think about it, is probably going to be more likely to happen depending on some intrinsic characteristic of the ball, because some may be more fragile than others, some are more resistant, some are just in a worse shape. So somehow something that depends on the specificity of the object. But then it's going to be important how many you have on the billiard table, because if there are many, the chances that they run into each other are going to be much higher. Then you may also consider that the speed at which they are running over the table is going to be quite a factor, because the faster they're going, the more kinetic energy they have. Therefore, the collision is going to be more powerful. This for the same reason, a car accident, if the car is traveling faster, is going to be more disastrous than if the car is going very slowly. Actually, it goes with as you know, the kinetic energy goes with the square of the velocity. So for a small amount of velocity, you have quite a lot of quite an increase in the energy. Another factor could be the orientation, because if the crack is just on one side of the ball, we may think that maybe the breakage happens only if the ball is traveling crack front. So with the lesion, with the defect in the structure on the front of the ball where it's going to collide with the other one. So orientation may also have a factor. And this is a good model for chemical reaction as well. All these factors are going to have a role in the speed of reaction. Today is going to be movie day because we have quite a lot of movie to watch. So this is another one. So follow the link to get to the video and then come back. And while you are at it, you can get maybe some popcorn, some pizza, because there's going to be more movie coming. See you later. So in the video, you have heard about the concept of activation energy. So let's try to understand better what this is about. So this is an energy diagram, and you will see quite a lot of those. And that shows you on the x-axis, it shows you the reaction progress. So basically it's a timeline, right? So you know that you're starting from the reactant, and then you're going to make the products. The thing is, the transition between reactant and products is not a direct path. So it's not like you go directly from this to that. You have to go through, you have to overcome an obstacle before you actually are able to perform the reaction. And this obstacle is sort of a hill that you need to overcome before you go on the other side. And what you have here is the transition state. So the transition state is this sort of a blob of all the atoms connected to each other. But as you can see, the bonds are not represented with solid lines, but they are represented with dotted lines. That means that those bonds are partial. They're kind of in the process of either forming or breaking. That's why bromine has two bonds coming out of it, while normally bromine can only make one bond. So this is a state that's highly unstable, and you can tell because it has a lot of energy. In these diagrams, the higher is a substance, the more energy it has, the more unstable it is. So you wouldn't be able to isolate this, to purify it, put it in a nice bottles and store it in the lab. Normally, only reactant and products can be isolated. So this amount of energy that I need to provide to my reactant before it's actually able to go downhill is going to be the activation energy. In the process of going downhill, it's going to give me back the same amount of energy. So here is absorbing activation energy. Going down here, that same amount is released. And then there is a net release of energy. That is the difference between these two levels. So this delta E. This is the difference in energy between products and reactants. So this is telling me that the reaction is exothermic because my products have less energy than the reactant. Where did that missing energy go? It went into the surrounding. So it was released outside. So this, let's say, comparing this activation energy to a hill is kind of a useful way to look at the energy diagram. It can kind of make sense in a more, using something more tangible. And so I like to use this example. So let's say we are in Wisconsin, where, as you know, people really like beer. So we have a village and we have a tavern where you can go on Saturday night and well, when they will be open again, and get some beer, right? But the problem is, you would think that the going from the village to the tavern is downhill. So at least going there should be a pretty easy process. However, there is a hill in between the two. So the only way to go from the village to the tavern is for these people to go up the hill, to climb the hill, and that of course requires some energy. So of all the inhabitants here in the village, there are some that are not so fit, and those are the ones that are represented with the color yellow and red and are a little bit smaller. And then there is the blue one. He went to the gym, so he's really fit, and he can go from on the other side. So from the perspective of the business owner, if only one person can cross, so that's only 1/3. The amount of people that are coming, if only the fittest can go on the other side, the actual amount of people that can go, let's say, every hour to the tavern is pretty limited, and the business is going to be pretty slow. So if the guy wants to make more money and wants to increase the business, he needs to have more people being able to go on the other side. So the possibility would be to dig a tunnel, right? So that's what a catalyst does. It increases the speed by providing an alternate path. The original path is still there. The hill is still there. If you want to climb it, you can do that. But the catalyst has provided an easier way to go from the other side, therefore making it available to everyone, and the speed of the reaction will go up. Many times you can read that the catalyst decreases the activation energy. That's not entirely correct, because the original path is still available with the same activation energy, but the catalyst is actually providing a different path with lower activation energy. Saying that it decreases the original activation energy would be not like digging a tunnel, but it would be like blowing up the whole hill with dynamite. Okay, and that's not what the catalyst does. Okay, so here we go with another movie. So hopefully you got your popcorn and you're ready to go. We will come back after this. So we have seen that in order to be able to get to the product side, first you need to go through you need to be able to get to the top of the hill. That would be the transition complex. And to do that, you need to have enough energy. So here you see an example of a distribution, right? This is a distribution of height. So we kind of know that men on average are taller than women. So the distribution of the height, I can build an histogram. On the x-axis, I have the frequency, the number of people with a certain height. And on the x-axis, I have the actual height. So I see that the distribution is fairly symmetric, meaning if I draw a line where the average is, the left side of the distribution looks pretty much like the right side. So that would be what is called a normal distribution. For men, there is the distribution is moved to the right is also kind of lower, so there is more spread. If I want to know how many men are, let's say, taller than 75 inches, I could draw a line here, and then the area under the histogram from that point on is going to give me the number of individuals that are 75 inches tall or more. So that's kind of a convenient feature of this sort of histogram. So this is the distribution of the average kinetic energy of the molecule, right? So we know that the kinetic energy is proportional to the temperature in Kelvin. That's an average level. Then there is going to be some molecule that has a little bit less energy and some that has a little bit more energy. For the same reason, like some people are taller than the average and some people are shorter than the average. So we can build a distribution where on the y-axis we have the number of particles that have a certain level of energy, and the energy is on the x-axis. And then we take a specific amount of energy. Let's take it equal to the activation energy that's necessary for the reaction to happen. The area under the curve from energy equal to EA on is going to give us the fraction of molecules that actually have enough energy to perform the reaction. So in this case, it's quite a minority respect to of the overall number of molecules. You can see that this distribution kind of look a bit like the one for height. It's more asymmetric, right? So the average is probably going to be not what you would expect it here, but it's probably going to be more in this point of the distribution. And so it's a distribution that's skewed towards higher value. So what happens if we increase the temperature? If we increase the temperature, we get a distribution that's more that's shifted to the right and is also more flat. Okay, so the first distribution, the blue one, T1, is for a colder temperature and T2 is for a higher temperature. So you see that the red distribution, it's more spread, is lower, and it has a larger amount of molecule with high energy. So the area in red is going to be larger than the area in blue for the same level of energy. So there are more in the red distribution, there are more molecules with energy equal or larger than the activation energy. Therefore, the reaction at the temperature T2 is going to be faster. Okay, here we go with another movie. So see you after the movie. So let's go back to the reaction rate, right? The rate is the change in concentration of a species in a certain amount of time. So for example, we could measure the change in the concentration of the products over time. Let's just remember that whenever we see a formula in between square brackets, what that means is that's a number and that's a molarity. So that's a molar concentration of that species. So the reaction rate, there are different types actually. There is the instantaneous and the average rate, like the same that you could measure for a car, like a car that's moving over on a highway. And when you just go by total amount of time and total amount of miles travel, that's the average rate over the whole trip. But at different points during the trip, the car could have been stopped, or the car could have been speeding. So the actual instantaneous rate at each time could have been very different. Then there is the relative rate. So for example, I could express the rate at which the products are appearing relatively to the rate at which the reactants are disappearing. Or if I have two products, I could be interested in expressing the relative rate of one of the two products respect to the other. Then there are rate laws or rate expression, those or differential rates that is telling me how the rate is influenced by the concentration of the reactant. And finally, we have the integrated rate laws, and those are used to calculate how much of the product I can make in a certain amount of time, or how much of the reactant would disappear in a certain amount of time. So we're going to go over those one at a time. So let's start with instantaneous rate. So this graph is showing us the rate of reaction over time for a particular reaction. So you see that it's not a linear relationship, it's a curve. In each instant, the rate corresponds to the slope of the curve. That could be measured graphically, for example. So this is the concentration of a reactant, and we can tell because it's going down, right? So the slope is negative. And you can see that the rate is getting slower and slower as the time goes by. So at the beginning, you have the maximum rate, and then the slope is getting smaller and smaller after the time passing. And this could be explained because if we have a reaction that to happen needs to have the collision between two molecules, as the concentration of the reactants goes down, it gets harder and harder for two molecules to run into each other. So it kind of makes sense that based on this scenario, the rate should go down. Now, the thing is, scenarios can be different, so things are a little bit more complicated than that. If I would be measuring the products, their concentration would go up, then the rate would be positive. The slope would be positive. As I was saying, the actual effect of changing the concentration of the reactants on the overall rate is quite complicated because it depends on what actually is happening. So, and there are many possible different scenarios. So for example, in this first example, you have a diatomic molecule that's splitting into the single atoms, right? So if we have a certain concentration, let's say one molecule, we expect to form two products, but things should not be really different if I double the amount of the reactants, because I would also make twice as many products. So basically it's a direct proportionality between concentration of the reactant and amount of products made. But things are different in this example where I have two molecules, the purple and the green, they need to collide and form the product. So if I have one molecule of each, there is only one possible collision that would be fruitful. But if I double the concentration of both, I have 4 times the number of collisions that I had before. So I'm increasing much more the rate of the reaction. So depending on what is the actual mechanism of the reaction, that typically I don't know a priori. The effect on the concentration could be quite different. The effect of changing concentration could be quite different. So as we were saying, the instantaneous rate is the rate at a particular moment and can be determined as graphically as the slope, the tangent, the slope of the tangent to the curve in that point. Now, because it's a graphical determination, that's not the typical question you get in a multiple choice exam, right? Okay, so this is the last movie. So you can watch the movie and then you can come back for the next PowerPoint presentation.